February 24th, 2008. YouTube engineers start seeing something strange in their traffic data. Requests from around the world are dropping, then more drop, then nearly all of them. Within minutes, YouTube is effectively unreachable from most of the internet. 2 hours pass before the problem is fully resolved. Nobody attacked YouTube's servers. Nobody hacked their infrastructure. YouTube's systems were running perfectly. The problem wasn't at YouTube at all. It was in the routing layer, in the system that tells the rest of the internet how to find YouTube in the first place. And the cause was a single misconfiguration, made by a telecommunications company in Pakistan that most people outside the networking world had never heard of, trying to do something completely unrelated to YouTube's global availability. To understand how that's even possible, how one company's local mistake could take down a global service for millions of people, you need to understand how the internet decides where to send traffic. And more specifically, you need to understand a protocol called BGP and a vulnerability at its very core. Start with a question that seems simple but isn't. How does your data know how to get from your device to YouTube's servers? We've established in earlier videos that the internet isn't one network, it's tens of thousands of separate networks, each operated independently, stitched together into something that behaves like one coherent whole. Your home network connects to your ISP's network. Your ISP connects to larger networks. Those connect to even larger ones. And somewhere in that web of interconnected networks, YouTube servers sit inside Google's network. For your traffic to reach YouTube, every network along the path needs to know Google's network is reachable, and here's the direction to send traffic to get there. The protocol that distributes this knowledge across the entire internet is BGP, the Border Gateway Protocol. It's the routing protocol that organizations use to announce to the rest of the internet what address ranges they're responsible for, and to learn what address ranges everyone else is responsible for. When Google connects to the internet, they use BGP to announce the address range 28.65.153.024 belongs to us. If you have traffic for any address in that range, send it our way. That announcement propagates through the global BGP system, from Google's direct neighbors, to their neighbors, to their neighbors, until every router connected to the internet has heard it and knows that traffic for YouTube's addresses should ultimately be directed toward Google. This is how the internet maintains its global routing table, not through any central authority, not through any single database. Through BGP announcements, propagating peer-to-peer across tens of thousands of networks, building a distributed, collectively maintained map of who owns what address space. And here is the vulnerability that makes the Pakistan Telecom incident possible. BGP has no built-in mechanism to verify that an announcement is true. When a network announces, "I own this address range," the rest of the internet has no automatic way to check whether that claim is legitimate. BGP was designed in an era when the internet was small, and the organizations connected to it were known and trusted. The protocol was built on the assumption that if a network says it owns an address range, it probably does. That assumption made sense in 1989. Applied to a global internet of hundreds of thousands of networks, it is a profound and consequential vulnerability. Now let's look at what Pakistan Telecom actually did. In February 2008, the Pakistani government ordered ISPs to block access to YouTube. The platform had published content the government considered offensive. Pakistan Telecom, one of the country's major carriers, implemented the block using a standard technique. They created a BGP route for YouTube's address range that pointed to a dead end inside their own network. Traffic from their customers heading for YouTube would be directed into a black hole, a router that simply discarded it. Effectively blocked. This is a legitimate technique for blocking traffic within your own network. The critical detail is that it's supposed to stay within your own network. It should only affect your own customers, not the global internet. What Pakistan Telecom did, through misconfiguration, was announce that route to their upstream providers, the larger networks they connected to for global internet access. Instead of keeping the YouTube block internal, they accidentally broadcast to the wider internet, "Send YouTube traffic to us." Their announcement said Pakistan Telecom could reach YouTube's address range. Specifically, they announced a more specific prefix than Google's existing announcement. Remember the longest prefix match rule from the routing table video. When two routes cover the same destination, the more specific one wins. Pakistan Telecom's announcement was more specific than Google's, so routers that heard both announcements chose Pakistan Telecom's route. Their upstream provider, PCCW, a major Hong Kong-based carrier, received the announcement and, rather than filtering it, propagated it to their own global network. From PCCW, it spread further. Within minutes, a significant portion of the global internet's routers had updated their tables to reach YouTube, send traffic toward Pakistan Telecom. Traffic from around the world began flowing toward Pakistan Telecom's network, into the black hole they'd created to block YouTube for their own customers. Gone. YouTube didn't disappear because of anything that happened at YouTube. It disappeared because the global routing system, functioning exactly as designed, followed what looked like a legitimate routing announcement, and that announcement pointed to a dead end. The timeline of what happened next reveals something important about both the vulnerability and the way the internet self-corrects. Within minutes of Pakistan Telecom's route propagating, network engineers around the world started noticing. BGP anomaly detection systems, tools that monitor the global routing table for unexpected changes, began firing alerts. Engineers at YouTube and Google saw traffic collapsing. Network operations centers started investigating. The fix, once identified, was conceptually simple. Pakistan Telecom needed to withdraw the rogue route announcement, or their upstream provider needed to filter it. PCCW, once contacted, withdrew the route from their global network. The bogus announcement stopped propagating. Routers around the world, no longer receiving Pakistan Telecom's more specific announcement, fell back to Google's legitimate route. Traffic began flowing correctly again. Start to finish, approximately 2 hours. 2 hours during which YouTube was unreachable for users across dozens of countries. 2 hours caused by a misconfiguration, propagated by a failure to filter, and sustained by a protocol with no mechanism to distinguish legitimate announcements from illegitimate ones. The most striking thing about this timeline is not how long it took to resolve. It's how quickly it happened in the first place. From misconfiguration to global impact, minutes. The same property of BGP that makes it fast and efficient at distributing routing information. The rapid propagation of announcements across thousands of networks also makes it fast and efficient at distributing incorrect information. There is no pause for verification, no checkpoint that asks, does this announcement make sense? The announcement travels at the speed of BGP propagation, and BGP propagation is fast. Pakistan Telecom's incident was accidental, but the same mechanism, announcing address space you don't own, or more specifically announcing a more specific prefix to attract traffic, can be done deliberately. And it has been. In 2010, China Telecom briefly announced routes for tens of thousands of IP prefix belonging to organizations around the world, including US government agencies and major corporations. For approximately 18 minutes, a significant slice of global internet traffic was redirected through China Telecom's network. Whether accidental or intentional has never been definitively established publicly. But the technical mechanism was identical to what Pakistan Telecom did, more specific route announcements, accepted and propagated without verification. In 2022, a BGP hijack redirected traffic intended for a major cryptocurrency platform. In this case, the attacker used the hijack to intercept traffic, steal credentials, and drain accounts, demonstrating that BGP hijacking isn't just about taking services offline. It can be used for interception, for surveillance, for theft. Traffic redirected to an attacker-controlled network can be read, modified, and returned to its destination, with the victim having no indication that anything was wrong. These incidents share a common thread. They all exploited the same fundamental gap. BGP routers accept announcements from their neighbors and propagate them based on policy and preference, not based on any cryptographic proof that the announcer actually has the right to make the announcement. So why hasn't this been fixed? The technical solution has been known for years. It's called RPKI, Resource Public Key Infrastructure. The idea is straightforward. The organizations that legitimately own IP address space cryptographically sign their ownership. Routers can then verify BGP announcements against these signed records, rejecting any announcement that claims ownership of address space the announcer doesn't have a valid signature for. A Pakistan Telecom-style incident would be blocked at the first router that validated the RPKI record, because Pakistan Telecom has no valid signature for YouTube's address space. The announcement would be rejected rather than propagated. RPKI exists. It works. Adoption has been growing steadily, particularly among large network operators. Major internet exchanges and carriers have implemented it. The global coverage of RPKI-validated routes has increased significantly in recent years. But adoption is not universal. And here's the catch. RPKI only works when the routers that receive a bogus announcement actually check the RPKI records and reject invalid routes. If a router in the propagation path doesn't check the signature, it accepts and propagates the announcement just as BGP always has. A chain of security is only as strong as its weakest link. And in a global system of hundreds of thousands of independently operated networks, there are many links that haven't yet implemented RPKI validation. This is the fundamental challenge of internet security improvements. You can't update the internet the way you update an app. There is no central authority that can push a security patch to every router simultaneously. Every network operator has to independently decide to implement RPKI validation, configure it correctly, and keep it maintained. Progress happens, but it happens gradually, voluntarily, and unevenly. The Pakistan Telecom incident sits at the intersection of two things that are both true about the internet simultaneously. The first is that the internet is remarkably resilient. It has no central point of control, no single authority, no master switch. It routes around failures, adapts to changes, and keeps functioning through an enormous variety of disruptions. The 2-hour YouTube outage resolved not because some authority fixed it, but because engineers at multiple organizations identified the problem, coordinated across organizational boundaries, and corrected it. The system, while vulnerable, is also self-correcting. The second is that the internet is built on trust in a way that has never fully scaled. BGP works because networks trust each other's announcements. That trust was reasonable when the internet was a small community of known institutions. At global scale, with hundreds of thousands of networks of wildly varying size, sophistication, and intention, that trust is a vulnerability, not a theoretical one. A demonstrated one, exploited repeatedly, sometimes accidentally, and sometimes deliberately. The distance between those two truths, resilient but vulnerable, distributed but fragile in specific ways, is where internet security lives. The Pakistan Telecom incident didn't reveal a new flaw. It made a known flaw visible in an undeniably dramatic way to an audience large enough that it couldn't be ignored. Next time you type a website's address and something loads, there's a routing system working invisibly underneath, a system of mutual trust between thousands of organizations, each accepting the other's word about what they own and where traffic should go. Most of the time, that trust is warranted. Most announcements are legitimate. Most routes are correct. Most, not all. And in the gap between most and all, incidents like this one are waiting.